IBM Research in Zurich. I'm a postdoctoral researcher, and today I'm going to give you a high-level overview of the main innovations behind this new software machine learning library that has been developed in Zurich over the last 3 years. Snap machine learning is a new framework for very fast training of linear models, generalized linear models. Training is extremely important for at least 3 use cases. First of all, you have real-time applications, real-time workloads, and you need to adapt your training model extremely fast to adapt to the new patterns in the incoming data, for instance. Or you want to find the right set of hyperparameters for your machine learning model, and in that case, you have to train multiple models with different sets of hyperparameters, and this is time-consuming. Also, recently in Kaggle competitions, maybe some of you are already familiar with this. Many winning models come from ensembles of models, and ensembles mean, so in ensembles you have to train different models, and again, you need to be very fast to exclude this bottleneck, this training bottleneck, from your machine learning pipeline. So this is the overview of the presentation today. I'm going to start with a short introduction about generalized linear models. I'm going to give you a high-level overview of the SnapML architecture. Then I will continue with very few details on the implementation side. And I will finalize with a few code examples for all the Python interfaces that we provide. And I will show you also some experimental results. So I'm pretty sure that regardless of your level of expertise in machine learning, I'm pretty sure that you are familiar, more or less familiar, with what linear models are. So you can think of, when we say generalized linear models, people usually think of a conventional linear regression. And such examples are, for instance, ridge regression, lasso regression, support vector machines for doing regression problems, or also logistic regression or support vector machines for doing resolving classification problems. So a linear model, you can think of a linear model as you have a response variable which is a linear combination of several predictors, continuous or categorical predictors. It is often the case, in order to not overfit model, it is often the case that you have to do regularization. And we do regularization in all these cases. For instance, support vector machines, ridge regression, logistic regression, we have L2 norm regularization, and for lasso regression, we have L1 norm regularization. Now, one interesting maybe difference between the ridge regression and lasso regression is that with lasso we can make the model even more interpretable than with ridge regression, because with lasso, if there are, for instance, features, predictors in your data set that are highly correlated, with lasso regression we can zero out the coefficients that correspond to these features. So you can only keep in your model a smaller set of features, making the model slightly more interpretable. So why are generalized linear models useful talking about recently and over the past years about neural networks, which are extremely useful for some applications, but also generalized linear models can be extremely useful. I was quite surprised in the beginning to see the result of this Campbell State of Data Science survey that asked 16,000 data scientists and machine learning engineers about what type of models they are using on a daily basis. And almost 65% answered with logistic regression, which is an example of a generalized linear model. And only 37 responded with the neural networks. So why are GLMs useful? There are multiple reasons. One of them we already addressed. It's about interpretability, the interpretability of your model. And this is becoming extremely important given the changes that have happened in the data protection regulation in Europe. As you might already know, there has been the GDPR has already been applied, and the European citizens have the right to obtain an explanation of a decision reached. So if you apply a machine learning model to a very sensitive field, like for instance healthcare, it is quite important, and it's becoming more and more regulated for you to be able, for you as a data scientist or as a machine learning engineer, to be able to justify why that model takes a certain decision. And linear models are inherently interpretable, because you have a set of features and each feature has a certain importance given by the coefficient assigned to that feature. So the higher the coefficient, the more important the feature is for the model decision. GLMs are also useful for other reasons, like fast training. We know that they are extremely scalable to large data sets with billions of examples and features. And towards the end, I'm going to also show you, part of the experimental results includes a data set with tens of millions of examples. And also, GLMs require less tuning. State-of-the-art algorithms for training linear models, they do not involve a so-called learning step parameter. State-of-the-art algorithms for solving optimization problems such as those like GLMs are coordinate descent, stochastic coordinate descent, or stochastic gradient descent. In stochastic gradient descent, you often have to tune very carefully the learning rate. Otherwise, it is quite challenging to find for your model to converge. With coordinate descent, you can have closed form solutions for each coordinate update. So less tuning. So what is snap machine learning? Snap machine learning is a machine learning software library that has been developed in IBM Research in Zurich. It enables very fast training of GLMs. Now, how does this library compare to existing machine learning libraries? I guess some of you, if not all of you, are already familiar with scikit-learn. Scikit-learn is a Python-based machine learning library for training machine learning models. It doesn't support GPU acceleration, even though it is able to call low-level C, C++ libraries such as liblinear for solving generalized linear models. It does not provide GPU acceleration. And if your system has a GPU, then you don't fully utilize your hardware resources. Also, scikit-learn is targeted at small to medium data size. So you can run scikit-learn on your single node, and you cannot use it to run it in a distributed manner using multiple nodes. So you cannot run it in a cluster. And on the positive side, scikit-learn has support for sparse data, not only for dense but also for sparse data. Scikit-learn is extremely popular also for other reasons. It has a lot of documentation, and it's quite easy to use because it has these Python interfaces. Then, if we move on to, there is also another framework called Apache Spark, and so this is the machine learning library provided by Apache Spark. It allows you, when compared with scikit-learn, to also run your training in a distributed manner. However, it does not natively support GPU acceleration. So again, you cannot fully utilize the resources of your system. And of course, there is another framework, TensorFlow. TensorFlow is much more generic than it's a much more generic framework. You can model various arithmetic operations as data flow graphs. But it's also very suitable for machine learning. It provides GPU acceleration. It can be used for distributed training. However, it's quite difficult to deal with sparse data sets. And now it comes our data set. Snap machine learning is not as generic as TensorFlow. At the moment, it only applies to generalized linear models. However, it provides GPU acceleration. It can be used in distributed environments, and it has full support for sparse data. So, now, how does the architecture of SnapML look like? The very fast training is achieved by taking advantage of different level of parallelism in your system. And this is extremely compatible with any cloud-based or data center-based environment. The first level, SnapML takes advantage of 3 levels of parallelism. The level 1 is data parallelism. So you can distribute your data across multiple workers. You distribute it and you divide it in partitions. Now, this is very important because it increases the memory capacity of your system. The second level of parallelism is that in each worker or in each node, you may have multiple GPUs and multiple CPUs. So you have to take advantage of the available GPUs in your system. And this is the second level. So SnapML is able to take advantage of the multiple GPUs that are connected via a very fast interconnect. And as we've seen, as we saw actually earlier in the morning, in power systems, we have the GPUs communicate through very fast links, these NV links, and we will show that SnapML takes full advantage of these links to accelerate the training. And the third level is inside each GPU, or inside each CPU. Because in both CPU and GPU, you have multiple multiprocessors, streaming multiprocessors, and in the GPU hardware. Also, and if you don't have a GPU, you probably have a multi-core system, multi-CPU system, and SnapML is able to run in a multi-threaded manner. So this is level 1. This is how the data can be partitioned across your nodes. This can be implemented using Spark or using MPI. We have tested both of them, both distributed computing frameworks. Now, this level of parallelism relies also on the COCOA framework. COCOA stands for Communication. It's a very long name. Communication Efficient Distributed Training Dual Coordinate Ascent. I hope I'm not mistaken. This is a framework that has been developed already for quite a few years. It's a set of algorithms actually, it's not a framework, it's not a distributed computing framework. COCOA can be implemented with Spark and MPI. COCOA is a set of algorithms to decide how to split the data across your nodes and what data is needed to be exchanged when you're doing the distributed training. Now, so SnapML implements a variant, an asynchronous variant of stochastic coordinate descent. When you do distributed training, you can run multiple iterations in each node before you actually synchronize the global model across all the nodes in your system. And here, the communication plays a very important role. So you may have the inter-node communication via, for instance, a 10 gigabit per second network. However, we know that in each single node, you may have much faster network links between the GPUs and between the CPU and the GPU. So your interest is to run as much as possible within one node before you do synchronization across the different nodes in your system. And SnapML does this. There are quite a few algorithms implemented. I'm not going to go into those into the details, but SnapML is able to take advantage of these heterogeneity of resources in your system, including different link bandwidths. So inside the GPU, at this, if you remember, we said we have 3 levels of parallelism. One is data parallel across workers. Then in each worker you have multiple GPUs, and then in each GPU you actually implement the asynchronous coordinate descent algorithm. So inside the GPU we provide we implemented an asynchronous variant of coordinate descent. For those interested in how this works, I highly recommend you to go and read this paper. that was published in Parallelism last year. We actually also have now a journal paper which should be available this year. Bless you. So how does the GPU algorithm works? So each local subtask can be solved effectively, as we said, using stochastic coordinate descent. What we do, we basically, because we have to make here, we have a GPU, so we have to make use of all the hardware resources provided by the GPU. So what we do for each coordinate, we assign each coordinate to a block of threads, and then the block of threads will, the blocks will actually run asynchronously, and they will run the coordinate descent algorithm. And then within each thread block, the coordinate update is computed using many tightly coupled threads. For the CPU, we have a different implementation. Many multi-core CPU implementations have been already proposed, the ones on the slides. What we implement is the algorithm so-called passcode, which comes with two variants. Is the passcode which guarantees convergence, and the wild passcode, which doesn't necessarily, it's very fast, but doesn't necessarily converge. We have implemented both of them, and later, when we have the demos, I'm going to use the wild passcode to see how it performs, which is not.
Excuse me, I didn't understand one thing. So, if you have a data set that has 1,000 features, you're doing computations for each of the gradients for each of the features separately.
Yes.
In one thread block each, so yes. 1,000 thread blocks.
Yes. Now, so that was one big, let's say, technical contribution that stands behind SnapML. So it's this what we call the GPU solver. Another important technical contribution is the dual HL algorithm. So you can think about this in the following way. Sometimes your data set or the data partition that has been assigned to your node doesn't necessarily fit in the memory of the GPU. So one way to address this, to do training on the data set, is to actually learn in batches. However, here we propose a different algorithm. And here what we do, so we use the so-called duality gap. So in short, we copy from the CPU to the GPU only the data points that are the most relevant. So we don't randomly choose data points, but we use the duality gap metric as a measure of the suboptimality of the model with respect to those data points. And we move only the data point, the most relevant data points, to the GPU, where the crunching and the asynchronous stochastic coordinate descent algorithm will run. And this approach highly accelerates the training. So how it works, you have in your main memory the local data, you have in the CPU the latest model, then you sample the points and compute the duality gap, and then you send to the GPU on a regular basis only the most relevant data points. And you update the data that resides in the GPU memory.
Is a duality gap something like a difference between a prediction and the actual, or I'm trying to get some intuition about what that is.
The duality gap, so you can solve an optimization problem using the primal formulation or the dual formulation. So they are equivalent. They give you some sort of bounds.
I see. And it's the gap between those two.
And that's the gap between the two. And if the gap is very large, it means that it makes sense to move those data points, and your training will mostly benefit from those data points. It's a whole theory behind it. And
does that help us? I was thinking if you move a partition of the data to one of these blocks and you're going to optimize for feature 1, maybe that batch of data doesn't inform that gradient, maybe it will inform other gradients, but not the one you're looking at. Does this help with that, or is that a problem at all?
So your question is probably you are influenced by the stochastic gradient descent algorithm.
Okay, yeah.
But this is stochastic coordinate descent. And the algorithm allows you to train one coordinate at a time, and they are like theoretical guarantees that you will get to the minimum of your objective function.
Okay.
So this is another very important technical contribution that currently is not part of the SnapML library, which will be available in a week from now. However, we are planning to extend the current version of SnapML to also include this kind of optimizations. I haven't mentioned this, and I think this makes sense. So SnapML at the moment is not provided for free. However, on the, I think, 22nd of June, there will be a technical preview of Power AI Enterprise, and SnapML will be available to try for free. So for those that are interested in running these models on their data sets to see how it performs, you could actually do it in this tech preview. Another technical contribution is what we call the streaming pipeline. The CPU-GPU link can often be a bottleneck, and it's often a bottleneck when you do training with data that doesn't fit entirely in the GPU memory. So what we try to optimize here is to, if we need to copy data from the CPU memory to the GPU memory, we try with the streaming pipeline to hide as much as possible the copy time. And the way we are implementing this is by using in the GPU, we divide the GPU memory into two buffers, an active buffer on which the training is performed and the swap buffer. And the CPU, when the CPU is copying data to the swap buffer without interrupting the training. So this is what you see here. You copy data, and at the same time, you do the training on the GPU. What you see here some additional boxes. These are related to random generators. This is a technical, this is like a detail in the dual HL algorithm that we just discussed. In this algorithm, the GPU has to perform some sorting of the coordinates. So we need to generate some random numbers. In GPU, this is quite ineffective. So we are generating the random numbers in the CPU, and we are copying the random numbers together with the data to the GPU. And then the GPU, by using device radix sort provided by the CUB library, we can sort these numbers, and we can get, actually, in this way, we can sort the coordinates in the active buffer. So that's why, if you're wondering what these boxes are, they are related to the algorithm. So, what interfaces SnapML provides today? The core of SnapML is implemented in C, C++, CUDA. It's a template library called libglm, and we built to attract users. We developed quite a few interfaces to make SnapML easy to use. And we will see in the demo, during the demos, how easy it is to actually implement a small script and to use SnapML. So we have three different interfaces. One is called SnapML Local, which is very similar to scikit-learn. This applies mainly to small to medium scale data. You want to do some prototyping, you have some small amounts of data sets on your single node system, and you want to do also you wanna make use of all the GPUs that you have in your system, so you can also do multi-GPU training. This Python API, this Python interface is fully compatible with scikit-learn. What it means is that you can use data pre-processing functions provided by scikit-learn. You can use scikit-learn metrics and so on. Then we also have, for distributed training, we have SnapML MPI and SnapML Spark. They both apply to large-scale data sets. SnapML MPI, probably you're quite familiar, given you're here in Barcelona Supercomputing systems, HPC environments. So we recommend the SnapML MPI interface for those that want to run distributed environments. It's very. We also provide a Python API, even though it's built on top of MPI. We provide a Python API. Basically, you use MPI once you write your script, which looks very similar to the one that you wrote with SnapML Local. You run MPI run, number of processes, your rank file, and then Python and the name of your script. And this is just as easy as this. And of course, we have SnapML Spark for those companies, for those institutions that already have environments with Apache Spark. This is just a Pi4J lightweight interface that interacts with libglm using the Java native interface. So code examples. I'm not going to spend too much time on these because anyway we have, after this presentation, we have I think 1 hour or 45 minutes to go through two examples, one local and one MPI. But just as an overview, you only need, if you have a scikit-learn already, an up and running scikit-learn Python script, you only have to change 2 lines of code to actually use the generalized linear models from SnapML. So you only have to import logistic regression, for instance, from SnapML, and then you have to call the constructor of the logistic regression model to create your model, and then you use exactly the same code as in scikit-learn. As you can see, the same applies for a SnapML MPI. There are a few differences when comparing this with the local version. One of them is the way you load the data. So we provide special loaders because you need to load the data in a distributed manner. So we provide loaders for distributed data loading. And also for the metrics, we don't use the scalar metrics. We calculate the metrics in a distributed manner. That's why we also provide, together with SnapML MPI library, several metrics, accuracy, hinge loss, and so on. And this is SnapML Spark, again extremely similar to the MPI example, just that when you run it with Spark submit, you provide a jar file and then your Python application. Now let's have a look. Yep, there's still enough time, I guess.
Yeah.
Let's go through the experimental results. Let me show you how SnapML compares to existing frameworks in terms of performance. Now, the data set that we used is quite, I think, is one of the largest data sets publicly available. It's called click-through rate dataset, Criteo dataset. It's a binary classification problem, and the main question is, will the user click this ad or not? This is quite important for many companies, as we might agree. We use we have two different data sets from Criteo. A small one with only 45 million examples and with 1 million features, in total about 40 gig, the size of the data set. And then we also have experiments with the full Criteo terabyte scale data set. This is with 4.2 billion and 1 million features. In total, the size of the data set about 3 terabytes. So here what you see is the single node performance. So here we use the small data set to be able to run it on one single node. As hardware, we used OnePOWER AC922 server, so the one that was presented in the morning. We know that this system provides 4 GPUs, however we only used one to make it comparable with TensorFlow. Because from our experiments, TensorFlow was performing worse when using multiple GPUs than when using one GPU. So to make the comparison fair, we only used one GPU. And of course, we have the NVLink interface between the CPU and the GPU.
So when you say that TensorFlow is the Power AI one, or?
I'm sorry?
When you say TensorFlow is the Power AI version, or is it the one that you get from this website?
It's not the Power AI version.
Yeah, it's probably the use.
It's the one,
the one that you can
the one that you can download. Yes. So we compare here. So the blue line is SnapML, and we compare it with scikit-learn and TensorFlow. Here on the x-axis you have the training time, and here you have the log loss, so the accuracy metric. And we are interested to see how long it takes to reach a certain log loss. So SnapML and TensorFlow, they are using GPUs. Scikit-learn doesn't use GPUs because it doesn't provide GPU support. It uses liblinear, which is single-threaded. Now, first of all, what's interesting is that the result that we got with scikit-learn is better than the one obtained with TensorFlow. And I think this is because TensorFlow works in batches. And this might be the bottleneck in TensorFlow.
What do you mean by batch? It's like many
so
small
this
cells?
data set doesn't fit in the GPU memory. So TensorFlow, the way it doesn't use technical tricks like we did with the Joule HL,
Right.
so it runs in batches, and it does the training in batches. So what we see here that a very encouraging result is that SnapML is actually orders of magnitude faster than the existing frameworks. We were very glad to actually get such a result.
Sorry,
Yes?
this order of magnitude is comparing one GPU to one core, comparing two GPUs. Is SnapML running on one GPU?
SnapML is running on one GPU. TensorFlow is running on one GPU, so it's apples with apples. Scikit-learn is one CPU. Because this is how it runs. I mean, we cannot configure it to work on multiple CPUs or on GPU. We just used existing frameworks to see how SnapML performs.
Given the sparsity of the data set, how your model generalize, since you are kind of doing this selection of data points in order to be faster, let's say. If you take your model, you will use new data to predict them, what is the accuracy?
If you use new data,
You testing set.
this is the test.
This on the test. Okay.
This is the test. This is not the training set. That's why it's written here. We have test. So we trained. Yes, I should have mentioned this. So I took the Criteo data set. We did the split 75%, 25%. We trained the model on 75%, and here we report the test logs.
What is each of the points?
Like iterations.
One iteration, two iterations, three
Yes,
iterations.
yes,
Like that. Okay.
yes.
It seems like the scikit-learn, even though it's all overall slower, it does reach
Very
a
fast.
plateau very fast, while
Yes.
yours seems that might be some.
That's a log scale too, right?
It's a log scale, yeah.
So you think that it's
so
not?
it's more compressed on a scale.
I see.
Madam, can I have a question?
Yes.
And this in your version is using the algorithm version that does not use the higher of the levels of concurrency that you described.
Here what we implement in this version, we had the streaming pipeline, the CPU, GPU streaming pipeline, and we have the GPU solver. So we have the twice parallel asynchronous stochastic coordinate descent. This is without the Joule HL. We were also interested to see how relevant is the NV link in this scenario, and we profiled the application on two systems. So we ran the same application, we did the same training on the same data set. However, on two different hardware systems. One of them was an x86, I think it was a Xeon 2.7 gigahertz, and the other one was the power system, the AC922, with the NVLink. Now, x86 for the CPU-GPU link, it uses the PCI Gen 3, and Power 9, the NVLink. So these are the results that we got, the profiling results that we got for the x86 system. And as you can see, it is very difficult to actually hide the copy data time. The training finishes, and then the GPU will idle until the new chunk will be moved into the GPU memory. However, and you see in total here it takes about 300 milliseconds. When we go to the power system, we get a completely different picture. So as you can see, the copy time is completely hidden by the training, and the time of one iteration has dropped from 330 milliseconds to 93 milliseconds. So you can highly benefit from the NVLink.
I haven't seen that one before.
This is another type of experiments. Here we want to show how important it is to do iterations local to your node instead of communicating as much as possible over over the network of your system. So here, this is we defined a certain suboptimality or a certain accuracy metric, and we measured the training time that it takes to get to that accuracy metric. So each one and each point here corresponds to a certain number of intranode iterations that benefit from the NVLink power. And we see that when you have a very fast network, the blue line, when you have a very fast network of, that connects your nodes, you don't have too much benefit. However, when your network is very slow, I think here, yes, it was 1 gigabit Ethernet, doing these intranode iterations can significantly happen.
Can you give me an intuition of what does it mean in training that you have more intranode iterations, that the training is more, you're looking at gradients more locally or something?
Yes, yes. So you have only a limited view of your data, of the data.
Limited because of in names of in features or in examples?
Can be in both.
In both.
Can be in both. Because if you remember, we had the first level of parallelism. And that's
data. You have data parallelism.
Yes.
And that's the first level.
That's the first level. And once you do the partitioning of your data across your nodes, then you will have a limited view of your data for the rest of the training. This will be fixed.
So the first part would be stochastic, the stochastic part, and the other one would be just looking at your chunk. So if you have more intranode iterations, means, what is it, smaller top-level partitions?
If you have more intranode iterations, it means that you are searching locally as much as possible for the minimum of your function. However, you cannot do it infinitely, because then you will overfit on this limited amount of data that you have.
Yeah, okay.
So there is a trade-off at some point.
Yeah, because some other thread block is finding very nice gradients for something, and you are ignoring them looking at your own piece.
Right.
So there's a trade-off.
There is a trade-off. And you see, if you do only one intranode iteration, it means that after each iteration you have to go through the whole network to synchronize your model. And this is a communication bottleneck. It brings additional delay in your training process.
That's what the scikit-learn thing would do.
Scikit-learn doesn't run distributed.
Right, but it would be equivalent to doing the first.
To one, yes. One
Takes
node,
longer,
one.
but maybe goes more direct towards the.
And it would have the full amount of data, scikit-learn, access to the full amount of data, not only to. Yes?
Does the plot say that if you are careful and you avoid going into the overfitting region, you can live with a slow network?
Yes. Yeah.
Is that the
Yes.
message?
I mean, sometimes in your cloud system or in your data center, you have heterogeneous resources, right? You have different types of networks. Maybe it's very expensive to have an HPC type of network when you're renting some resources in the cloud. So based on your budget, maybe you want to go for a network which is not as fast as an HPC type of network. So probably you would go on for a 1 gigabit Ethernet. And in that case, even though that network is slow, with these technical details with SnapML, we can still very fast train a model by taking advantage of the local resources. And this is the last slide with results. This is on the terabyte scale benchmark. So this is on the 4.2 billion example dataset, critical dataset. On the x-axis, we have the training time in logarithmic scale, and on the y-axis, we have the log loss on the test dataset. And here we plot results that have been reported in different articles. We couldn't run all of these. We couldn't reproduce all of these results. So these are results reported in existing publications. So what we have here, we have linear, and in this case they used a single machine, 1 core, and they implement also coordinate descent. TensorFlow, this was TensorFlow ran. This was actually ran. We reproduced this result. It's TensorFlow ran on 16 V100 GPUs that matches the hardware scenario that we use for SnapML. TensorFlow here, this is another result reported with 60 worker machines. This is TensorFlow on Spark with 12 machines. And these are Spark, MLlib, and Valpal Rabbit. On Valpal Rabbit was on a single machine with 12 cores, and this was run on a cluster. Not sure with how many machines. All of these, they implement coordinate descent, like SnapML. They implement something else. However, we see that SnapML it's about 46x faster than the closest competitor, which happens in this case to be TensorFlow, even on a terabyte scale benchmark. And with this, I would like to conclude. So this is the work of many people, even more people now, in Zurich. And SnapML, again, will be available to try for free as part of IBM Power AI, June 22nd. Yeah, we would be happy to hear if anybody in this room would be interested in using our software framework. With this, I would like to thank you. Getting our hands dirty. I'm gonna show you 2 examples, one for the local interface and one for the MPI interface. If you remember, we had the core, libGLM, and then 3 different interfaces, local, MPI, and Spark. For the MPI, I'm going to use 2 P9 machines. So this is a system, I'm going to use a P9 system that we are using in Zurich. And I'm going to start with the local example, the one that is very similar to scikit-learn. As data set, I'm going to use the same data set for both examples. One is the same data set, the Criteo Kaggle 2014. I don't remember by heart the number of features, and it was in the presentation. So what I'm going to do, I'm going to guide you through the Python script and how we write it. So this is, and then I'm going to run it, and we'll see the training times, and we can also check with NVIDIA SMI, for instance, we can check how the GPUs are working and so on. So let's start with the local example. So first of all, what we need to do, after we download the data, which is publicly available, we need to pre-process it. To pre-process it, first of all, we need, can I use the pointer, maybe?
Yeah, you have to use the pen drive. Pull
Yeah.
the.
It's green. Yeah.
Oh, okay. Not that. Pointer.
So, first of all, after we downloaded the data, we need to read it. Now, the data is in libSVM format, so we need to import the load.svm-like file function from sklearn datasets, and we can use it by passing the path to the dataset. What it returns are are x and y. This is the dataset examples, and these are the examples with the features, and y is a NumPy array with the labels for all the examples in X. Now, the next step is we want to split the data in train and test. So how do we do it? Again, we use scikit-learn functions. So we use the train test split on the previously loaded X and Y, and we split X and Y using 0.25 test size. What it means is that 25% of X will be the test set and 75% will be the train set. And here we use a random state just to be able to reproduce the results. Now, what train test split returns is the X train X test, Y train Y test. So the training data set and the test data set. Now, we could already start doing the training. There is some additional pre-processing that we are doing here. And this is just to accelerate the loading of the data if you want to try, for instance, to train a logistic regression in SnapML with multiple sets of hyperparameters. You don't want to incur every time the same loading delay latency. So what we do here, we save the train and test data sets as binary files, and for the labels, we save them as binary NumPy arrays in these files. So this is the pre-processing. This is like a pre-processing script, and we are going to use these files to load the data in the training script. So this is just the first step, let's call it. This is already done, so I'm not going to run it because load.svm-like file is quite slow. It's very slow, and this is a big data set, so we don't want to wait now for just for data reading.
Which goes back to the earlier points about NVMe and
Yes.
storage bandwidth and all that stuff.
Oh, yeah.
Right. So this was the pre-processing script, and now let's go to the core. I don't like this color scheme. Let's change it. All right. So what do we do now? So after running the data pre-processing step, we can load the data into memory by reading it from the files, from the binary files. And this is what we do here, using the load and reset functions from SciPy. So as you see, until now, we haven't used SnapML at all. That's why we say that SnapML is fully compatible with scikit-learn. So now is the first time that we will use NapML. So CRITIO, as you said, is a binary classification problem, and we would like to train a logistic regression model on this data set. So what we do, we import logistic regression from the SnapML package, and then we create our logistic regression model by calling it in constructor with several parameters. And this will return your model that then will be used for training. Now here you have some parameters that you need to set. Of course, we have default values, but ideally you want to control these parameters. So you want to run the training on the GPU. So you set use GPU to true. And then you want to run the training on multiple GPUs. Now here we have a P9 machine with 4 V100 GPUs. So we can use all of them, all 4. It's very easy to identify or to instruct the logistic regression model from SnapML how to use the GPUs. So you set the device IDs parameters to a list of IDs. And these IDs, they correspond to the GPU IDs. And the last one is the number of iterations that you want to run. How many iterations for your coordinate descent algorithm you want to run to get as close as possible to a converged model. Yes.
Here you specify the resources you are going to use.
Yes.
For the whole run.
For the whole run.
For the whole run.
Yes.
So how malleable is the environment, or is this something that depends on your environment, or depends on the underlying infrastructure, or it is not malleable at all?
You mean how flexible this is? If it's able to automatically identify on which resources?
No, my question is if this is something that is going to be running for 10 hours, and after 2 hours I might want to do another small thing using 2 GPUs, can somebody shrink your 4 GPUs here to 2 GPUs for a while, and then go back to
At this
4
moment,
GPUs?
no. At this moment, no. So here the assumption is that you have your GPUs fully dedicated. Of course, somebody else can use them, but it will impact your training time. So once created, we can now run, like in scikit-learn, we can call the fit function on the training data set, and we also need to provide, because it's supervised learning, we also need to provide the labels of your training set. And so this line here is actually running the training, and it's using the four GPUs. Now, once trained, we have to run inference. So we want to get our predictions on the test data set. And for this, we provide several functions. In this case, we use the predict probability function, as you find it also in scikit-learn. And this one, because it's a binary classification problem, this will return to you the probabilities corresponding to the 2 classes for each of the examples in your test data set. And then with these predictions, you can call any scikit-learn metrics, such as in this case the log loss, by providing the true labels in your test data set and your predicted probabilities using the train model, the logistic regression model. So, alright, it's not over yet. this was the GPU training. Now I also want to guide you through how to run logistic regression on CPU when, for instance, you don't have GPU in your system. So here, this is again, you have to instantiate your logistic regression. Instead of and by setting use GPU to false this time, you're using the CPU. You're setting also the number of iterations, and here, if you want to run the multi-threaded implementation, the passcode while implementation of coordinate descent, asynchronous coordinate descent, you can specify using the num_threads parameter how many threads you want to use for running the training. And then basically the rest is exactly the same as we had before with GPU. You run the training again, you predict your probabilities, and you calculate the log loss.
Main question.
Yes.
This is here you're specifying only the concurrency at the level, at the lowest level. When you mentioned in your presentation the 3 levels, you are not doing anything about the 2 top levels here.
No, this is the level
next.
3. Yes, because this is the local implementation. There is no distributed training. And then we want to compare the results that we get with SnapML. We want to compare the performance with the one obtained with a scalar. Just as a comparison. So this is how you train a logistic regression model using sklearn. Now, how do you instantiate the logistic regression in sklearn? Now, if you would look at these 2 parameters, you would think that we tune them so that we get the best performance gap between SnapML and logistic regression, which is not true. If we would run logistic regression with the default parameters, so nothing, these 2 parameters would disappear. We would run logistic regression, assume you don't know anything about logistic regression, you don't know how to set those parameters in scikit-learn, then you would just say logistic regression parentheses. So you wouldn't set any parameters. And this one takes ages on this data set. Yeah, it took hours on this system. So we realized that by default, logistic regression is running the primal formulation of the optimization problem, which in this case is very inefficient because you have much more examples than the number of features. When you have much more examples than number of features, you want to run dual and not primal. When it's the opposite, you run primal. So in this case, we had to set dual to true. And in a linear model, you often have, so you have your features multiplied with coefficients, and you also have an intercept. We set it to false. Actually, this one actually doesn't influence the accuracy anyhow for this data set. But we set it to false to compare apples with apples, because in SnapML we don't have yet the intercept. We only have the coefficients of the features. So by setting these 2 parameters, we actually reduce significantly the training time of scikit-learn. And then the rest is the same. We fit it, predict probabilities, and apply the log loss. So this is the script. So this is how a Python script would look like if you want to run GPU training with SnapML or CPU training and compare it with scikit-learn. Now, let me run this one and see what we get.
clarity, you're running this somewhere else, right?
This is not here in BSC. This is an IBM system, a P9 AC922.
Right.
And now it's loading the data. The data is loaded from binary files, so this is going to be much faster than Logistic, right? It's going to take about 30 seconds. All right, so here I want to show you something very quickly. So now it's running the GPU training with the SnapML. And here I want to show you NVIDIA SMI. So what's going on? This is your exit. So NVIDIA SMI. Yeah, the training is already over. It was not very fast, but you would see, like, because we are running 4 GPUs, we are running training with 4 GPUs, you would see all the 4 GPUs occupied. The GPU training was, as you see here, 29 seconds, and this is the logarithmic loss that we obtained. And now it's running the CPU training. And on the CPU, if you remember, we had set the number of threads to 40. And as you can see, but they are not pinned. So here there are 2. There's not enough space to see all of them. So I just wanted to show you that there are 4 threads running 100%. Do we see them? Are there? We have 4?
Yes.
Yes. So 1, 2, 3, 4.
Question. This is with OpenMP
Yes.
or with OpenMP?
With OpenMP.
So you did program everything, you didn't call any library or any internal?
No, it's OpenMP. Yes. Yeah. So here we are implementing the passcode while implementation, which in theory doesn't guarantee convergence, but on all the data sets that we tested, it's getting very close to the accuracy that we get with the GPU solver or with scikit-learn. So we're gonna wait also for the CPU training to finish, and for scikit-learn, I will probably stop it and show you the result because it takes too long. It takes about 10 or 12 minutes to train on the same data set. So as you can see, there is already a 20x difference between the GPU and the scikit-learn.
I was wondering about what is supported in SnapML. So we see logistic regression. Do you have other? Is it the general linear models with any link function that you support?
So we have ridge regression, logistic regression, support vector machines.
Okay, support vector machines are done with generalized. I don't know the details. I didn't know they did them with gradient ascent.
We use the same algorithm, but we use the linear kernel in SVM. I mean, there are multiple kernels to convert.
So you can only use the linear one.
What we have in the SnapML is the linear kernel.
And do you have some function for example, like visualizing the importance of the features that you find?
This will be available in the next release in September.
Okay.
We also have for September, we have Lasso to make it's related to how interpretable the model is.
So you do, for instance, you do ridge regression, and can you do logistic ridge regression?
No.
Okay, so you don't. It's, yeah.
What do you mean by logistic?
Well, I think you can do the reach. Maybe I'm stepping out on a limb, but I think you can do the. Like in general, you can do a different link function, like the logistic one, and then a separate thing is that you do the regularization with the reach regression or a soup.
Ah.
Maybe I'm stepping out on a limb. I don't know.
No, so only these three: reach, regression, logistic, and support vector machine. In this technical review, June 22nd.
Because I guess the backend would allow, once you have everything, all the engineering set up,
Yes.
because
Yeah.
you don't have like a low-level interface to this backend.
No.
You need someone to code these logistic regression functions. You can't just.
We need to add new objective functions. But the library is very modular, so it's easy to. Once we have the formulas, just the formulas take a bit more to derive.
Ah, okay.
But once we have the formulas, then we implement them in the library, and that's straightforward.
Okay. So you have to derive different formulas.
Hmm?
You have to derive different formulas for your.
Yeah. You need the formulas, different formulas, different
Okay.
regularizations, and 1 and 2.
Okay.
So here we have the CPU finished as well. It took, as expected, more than the GPU. It achieved the same logarithmic loss as the as GPU, and now it's running the DSP learn. And I will stop it. And I can show you the result. Yeah, where was it? Here. So I ran it. It was on the same system. I ran it like a few hours ago before presenting. As you can see, the training time, 10 minutes, more than 10 minutes. All right. Any questions? All right.
So the slides and so on that you use,
Yes.
they can be shared.
I think so.
Yeah, I have already the slides, but anyway, yeah, sure.
Yeah.
No, but
I have to send you the slides.
yeah, the previous one presented by your manager to the.
You already have those.
But anyway,
Okay.
I need your slides actually, not his slides. I can forward to anyone. Yeah.
Okay. All right. Okay. So that was an example using a SnapML local. Now I'm gonna guide you through an MPI example with 2 machines. So this I need to grab another 2, and I need to go. Oh, so we're gonna use 2 machines. Let me go to another folder. This is MPI. We have multiple examples. Okay. We have examples, and we go to Criteo. All right. So this example will go again in 2 steps, like we did with the local example. The first step is pre-processing, and the second step is the actual training and prediction. So now, as you see, this is going to be very familiar to you now. We load the same data set using load SVM Lite. Then we split it exactly the same way as we did before, and then we save the data in binary format. Actually, this is something. There's something else here. So now, as you will see, I will compare the accuracy that we get with SnapML MPI2 machines with the one that we get with Scalar. And it's exactly the same as the one before. The comparison is, however, not apples with apples because scikit-learn is not running distributedly. However, just for comparison, I also ran scikit-learn. Now, for scikit-learn to accelerate the data loading, we had to save the data in binary files, and we could have done the same thing, well, not exactly. For SnapML, now in MPI we also provide like a snap format, which is extremely even faster than the binary files with the NumPy scipy. This is just a detail. We can move over to the example pretio.
Sorry, but when you do the preprocessing for the NDA version, is a different preprocessing than for the sequential version because you split the files? Or?
No, we could have used, actually, we introduced this a bit later. We could have used the same snap format also for the local. It's not a customized, distributed loader. It's just for very fast loading. And
So it's a form of data compression or something?
yes, it's data compression. Yes, especially good for sparse data sets, like a pretio.
My question is whether you are doing something like a domain decomposition here or
No,
no?
no, nothing. No. I should have set my color scheme in. Okay, good. Alright. So what do we do? The assumption here is that for loading the data, the assumption is that we have a network, an NFS system, a network file shared system. So when in SnapML, when we read the data, we need to simply pass, yes, I can use the pointer. So we can simply pass the path to the snap, to the data set in snap format, and using load from using the load from snap format function provided in the loaders of SnapML MPI, we can load it in a distributed manner. What's behind it? It's very simple. It's each node will know there is an MPI-com rank, MPI-com size. You identify how many nodes you have, and based on the number of nodes and on your rank, you know which portion of the original data set you're going to do the training on. That's pretty much the whole philosophy.
Has there been any thought to do this with something like Loop or
With
HDFS? Or?
this could also be implemented with this, yes, but we don't have it at the moment. Now, after loading, what we need to do is to initialize the regression model from the SnapML MPI package. So the way we do it, again, similar to the local version, we have to define the number of iterations. You have to define whether you're running the dual or the primal. By default is dual, so the dual is dual, so this could actually go away. We want to use the GPU. So we set use GPU to true. We want to use each MPI process. There is one assumption that I need to mention here. So the assumption is, in order to get the most performance, is that you run one MPI process on a node. And that MPI process is fully utilizing all the GPUs provided by the system. So that's why we are running with GPU set to true, and we define here the devices that one MPI process will use on the node. So if we run it with two MPI processes, as we are going to do shortly, each MPI process will be assigned on a node, and each MPI process will use 4 GPUs. And this is the number of threads. This is not the number of CPU threads. If you remember, in the GPU solver, so the level 3 parallelism, we have to assign the coordinate to a block of threads. This is defining the size of the block. So you can also, the user can also have control on this parameter. It makes sense to play with this parameter when you have many features. It makes sense to increase the number of threads when you have more features in your data set.
So do you have to worry about the NOMA affinity between the GPUs?
That's a very tricky question. So it is extremely important to. It's extremely important. It influences the performance if you don't pin the processes to the right sockets and so on. At the moment, SnapML doesn't implement anything about ensuring NUMA locality. However, we have already implemented a solution that will be available in the next release. After defining the logistic regression model, the user again will run the fit function on the training dataset, and then it will run the prediction function. We said we have this predict probability. We also have predict. Predict already gives you the class. So the predict probability gives you the probabilities for each of the two classes. We ran both of them because we wanted to measure not only the log loss but also the accuracy score. And they receive as input different formats. So here we calculate the accuracy and the log loss. So that was GPU training. To run CPU training, again, very similar to the local version. You have to set the number of iterations. It's a dual problem, formulation problem. You don't want to use GPUs because you don't have GPUs. And you set the number of threads to, in this case, to 4. You do the same thing, you fit, you predict. You report the results. scalar. The same as before, loading the data from binary files. Then you have a scalar logistic regression with these two parameters set. You fit, predict, and estimate, calculate the accuracy score. Let's run it. So how do we run this script? All right. So we said we want to run this example on 2 nodes. So what we do, we call the MPI run. Yeah, in this case it's the full path because there are multiple OpenMPI installations on the system. You define the number of processes and then the machines on which you want to run the 2 processes. Then you call Python. I have an Anaconda 3 installation, and at the end you have the name of your Python script. So as you can see, even though it's running MPI underneath, this is extremely transparent to the user. So everything should be fine, and let's run it. So now you will see that the printing is done twice because we have 2 processes. I could have restricted the printing to only one of the racks. However, for this demonstration, it doesn't really matter. So now the model is being trained using the GPUs of the two P9 machines. And it's already over. Because now, as you can see, so training the model, it ran the prediction, and now it's training the model on CPUs. And we should see very soon, we should see the summary of the accuracy scores and the training times. Any other questions in the meanwhile?
Sorry, are you going to show Spark one?
No, no. Do you run Spark here? Do you run Spark in the...
No, maybe I don't run anything.
Carlos.
Back in the past. Back in the past.
Back in the past? Okay, okay.
Which means just maybe 6 months power.
I mean, from our experience, the Spark results were much worse than the MPI ones. I mean, because of the overheads in the software stack, it's much lower. Now, I thought that for an HPC environment like BSC, I thought that MPI would be much more interesting, so I don't have the Spark one, but yeah, I mean...
In terms of how it looks like, it's pretty similar to the MPI one, source code.
Yeah, it's very similar, very similar. So as you can see, the training is already done, and here we have the summary. It's very interesting here because we have this snap format, very compressed format in SnapML MPI. As you can see, it was extremely fast. In less than 2 seconds, we loaded the data. Then we have the GPU, the GPU and the CPU accuracy, and the GPU and the CPU log loss, and the as expected. This is the training time, the GPU and the CPU, and this is similar for the second MPI process. And now SPLN is running, and we know it takes about 10, 11 minutes to train. So this is, with this I would like to end the demos with SnapML. I hope you enjoyed these demos. Not very exciting, Python code, importing some